Homework 16, the central limit theorem for proportions, video 3. In the first video, we defined what we meant by proportion, both for a sample and a population. In the second video, we discussed a sampling distribution for proportions, for p-hat specifically, where we took all the proportions of a given sample size, calculated what percent of each one had a characteristic, and then formed the distribution for that. Which leads us to the central limit theorem for proportions, and it goes something like this. Let lowercase b be a population proportion, and lowercase n be a sample size. If two conditions are met, n times p is greater than or equal to 10, which means that more than 10 of the sample have a characteristic. Yes, sample size times the proportion. And n times 1 minus p is also greater than or equal to 10. By the way, if p is the proportion of a population that has a characteristic, then 1 minus p is the proportion of the population that does not have that characteristic. For example, if 40% of a population had a characteristic, 40% is the same as 0.4. 1 minus 0.4 is 0.6, or 60%. So 40% have a characteristic, the other 60% don't. But I digress. If n times p is greater than or equal to 10, meaning at least 10 in the sample would have the characteristic, and n times 1 minus p is greater than or equal to 10, meaning at least 10 in the sample would not have the characteristic, then the sampling distribution of p-hat is approximately normal. Makes a bell curve. We get to use the z-chart, as you'll see here momentarily. Plus, we can calculate the mean of that bell curve of that sampling distribution and its standard deviation, both of which are related to the values of p. The mean of the sampling distribution of p-hat, the variable is mu subscripted with the p-hat, which is read mu sub p-hat. That mu looks too much like an M. Give me 1 second. That's better. But the variable for the mean of all the p-hats is mu sub p-hat. And as we saw in the previous video, when we averaged all the p-hat values, it ended up equaling the population proportion. So it's a formula, but it's really more of an observation. This says if you average all the p-hats, you're going to get the same thing as whatever p equals. And then the formula for the standard deviation, well, first off, the variable for the standard deviation of all the p-hats is sigma sub p-hat, which makes sense. Sigma is standard deviation for a population, or in this case, all of the p-hats. And the formula for that is a tall square root with a fraction underneath it. The numerator is p times 1 minus p, and the denominator is n. So we have formulas for the mean and standard deviation of the sampling distribution of p-hat. We will be using these formulas when we do probability problems, which will take us to the z-chart, and we'll have a conversion formula that requires both of these values. But before we go there, let's just take a look at a real quick example. For example, in a population, let's say that p equals 0.25. So 25% of the population has some characteristic. If n equals 40, we're going to do 3 things. A, verify the sampling distribution of p-hat is normal. Well, let's start with that. To verify that the sampling distribution of p-hat is normal, we have to show that both of these things are true. So let's start with n times p. N times p is 40 times 0.25. That's exactly equal to 10, which is greater than or equal to 10. Check. But we also have to check n times 1 minus p. N times 1 minus p n is 40. Well, if p is 0.25, then 1 minus 0.25 is 0.75. So 25% of the population has a characteristic, the other 75% don't. 40 times 0.75 is 30, which of course is greater than or equal to 10. So that's all you have to do to verify that the p-hats are normally distributed, that their distribution would make a bell curve approximately. For part B, we're just going to calculate mu sub p-hat and sigma sub p-hat, the mean and the standard deviation of all the p-hats we could generate for the sample size of 40. And that's pretty easy. Mu sub p-hat is just equal to p, and p was just equal to 125. But sigma sub p-hat, that's actually a formula. You have to set something up. It's a square root. I like putting the denominator first. The denominator is n, so it's 40. The first number is p, which was 0.25. And the second number is 1 minus p, so 1 minus 0.25, which is still 0.75. So this would go into a calculator and come out very carefully. Looking for a calculator. Excuse me, I have to go over to my computer bag and get one out. There's one. Let's see. So, what I like to do in the sigma sub p-hat calculations is figure out the part under the square root first, and then just square root that answer. So, 0.25 times 0.75 divided by 40 equals, and then square root that. If we take it to 4 decimal places, we get 0.0685. This number will always be pretty small because the numerator is the product of two numbers less than 1. And then we divide that by something and then we square root it. So this will always come out to be a pretty small decimal. So how do we use this in proportion probability problems? Well, we'll take a look in the next video.